good. So we are live streaming. So, hello everyone. Welcome to the fourth TCSS talk of this term. Just a couple of organizational announcements. On Saturday, 21st of November, we are co-organizing an academic internship event together with Cambridge SciSoc and Oxford SciSoc. In this event, students are sharing experiences about their internships. We are looking for speakers for the internship event. If you had an interesting internship and you like to talk about it, please fill in the form which you can find at the bottom of the video description. Our today's speaker is Professor Michael Cates, the head of Soft Matter Research Group at Department of Applied Mathematics and Theoretical Physics here in Cambridge and the 19th Lucasian Professor of Mathematics. His research work focuses on the theory and modeling of soft matter, such as polymers, colloids, gels, liquid crystals, and so on. In today's talk, Professor Cates will be speaking about the transition from a flowable to a jammed state in dense suspensions upon increasing stress, such as that in cornstarch water suspension. This talk and the Q&A session will be recorded and later published on our channel. Please welcome Professor Michael Cates. Professor Cates, the stage is yours.
Thank you very much. Now, I'm getting a bit of an echo back from you at the moment. That's fine now, I think. Okay, shear thickening in dense suspensions. I'll say what these words mean as I go along. Let me start with this outline. So I'll talk about this phenomenon of shear thickening, which some of you will have experienced if you've ever played with cornstarch powder and water in your kitchen. So I'll say what we're trying to explain and then tell you roughly how we explain it. And then I'll move on to some applications of how this new knowledge, which has appeared over the last 5 or 6 years, can be useful, one of which involves chocolate. So that's something to look forward to later in the talk. I don't know if you brought your own chocolate. I should have advised people to bring their own chocolate. Only to eat, though. You won't be able to do any other experiments with it in this talk. And then I'll move on to some more recent work, if I have time, about how to understand the behavior of these dense suspensions under time-dependent conditions. So that's what we mean by beyond steady state. There's a connection with something called absorbing state physics, which I will, again, describe at the appropriate moment. And if there's time at the end, which there may not be, I'll say something about very recent work about what we call constitutive models. So this is building sets of equations that are capable of modeling the rather complicated behavior that I'm going to show you in the course of the talk. I should mention various collaborators. Their names are here. I'm not going to read them all out. Mathieu Viart, who's actually just moved from Lausanne to Singapore, is the main kind of conceptual co-author on the first part of the talk, as I will describe. Many of these other people have contributed to the more technical elements that I'll talk about a little later on. So first part then, steady state shear thing. Firstly, what is it and what are we trying to explain as we build mathematical models of the flow of these so-called dense suspensions? So before directly addressing that question, I want to remind or tell you about some basic physics of fluid flow. And the study of this topic dates back to Newton, who in his Principia wrote about the flow of a fluid. So the basic concepts we need are the idea of a stress and of a strain rate. So if you look at this green picture here, this is started as a cube of size h and has just been deformed by applying force F, which is the stress sigma times the area, which is h squared, of the top of this cube, shown by the right arrow here. I'm going to use my cursor to point at things from time to time. So if there's a force per unit area, sigma, that's the stress. It has a more complicated aspects. This one is in the direction of flow. So that's shown by this arrow here. And the system is having its shape changed. So what I'm really thinking of, for instance, is a fluid. And I have a fixed plate at the bottom and a moving plate at the top. And in a simple fluid, I get this linear distribution of velocities. So the velocity u to the right is something times h at the top times t, and it's proportional to the distance from the bottom. This something is called gamma dot. It's called the strain rate, and it's essentially the speed at which a fluid is changing its shape. So a fluid resists changes of shape with a force that depends on the rate of change of the shape. And Newton's insight all those years ago was that at least for simple fluids, and that means things like water and a whole bunch of others, which I'll mention in a minute, the stress is proportional to the strain rate. So there's a linear relationship between stress and how fast the fluid is moving. However, this is not like Newton's laws of physics. This is not something which is fundamental and has to be obeyed by everything. It's a characterization of a simple class of fluids, and this class is called Newtonian for obvious reasons. So in a Newtonian fluid, I have a stress sigma, which is linear in the strain rate called gamma dot, usually that's how that's pronounced, and the slope is eta, another Greek letter, lots of Greek letters, sorry, and that is called the viscosity, the slope. So that's what defines a Newtonian fluid, and these different curves here, and we'll come back to this later on, describes a bunch of different fluids, each with a different viscosity. So these could be, for instance, water at different temperatures between, say, 5 and 95 centigrade. It is possible, however, to have materials which are more complicated than that. And for obvious reasons, these are called non-Newtonian fluids, if they are indeed fluids at all. You can also have complicated forms of solid behavior, which would be a non-Hookean solid. But anyway, in general, these are described by what's called a flow curve. So the stress sigma is now a function of the rate of strain, the strain rate, which is no longer just a straight line with some slope. And this function can be pretty much anything. It can curve all over the place. And the case that we call shear thickening is when there's upward curvature in this plot here. So these two curves would both be called shear thickening. So that basically means that the slope of this curve is getting bigger at high strain rates. So the viscosity is going up the faster you push it. Whereas these ones here are shear thinning because it's curving downwards. So those are different types of non-Newtonian fluid. Over here on the Newtonian column, water is one I already mentioned. Olive oil is another. The liquid version of honey, not the solid one, obviously. And if you melt glass, that's also a Newtonian liquid. Of course, glasses can also be solid. I probably shouldn't have put that in that column. If I want examples of non-Newtonian liquids, well, if you put a bit of spit between your fingers and start shearing it with your fingertips, if you were able to turn that into a sufficiently precise measurement, you would see one of these funny shaped curves. The oil you put in the engine of a car is also such a thing. Things like putty, melted plastic, and the specific case I'm going to talk about today is dense suspensions. So non-Newtonian fluids. And in the dense suspension case, it's the shear thickening that I'm mostly interested in. So here's a couple of movies, which I hope you can see, of dense suspensions under flow. Now, the left-hand picture looks like a computer-generated movie, which of course it is. It's running on my computer, but that's actually real data. So what you see here is particles whose radius is about a micron. They're being subjected to this shear flow, as you can see by my blue arrows here. So this had the top plate moving, bottom plate stationary. Show that again. And they are obviously jiggling around. They're flowing. And they're doing this in a somewhat jerky way. And that's because these particles tend to jam. And the jamming of particles underlies most of what I'll be talking about in terms of the non-Newtonian behavior in this talk. This is a computer simulation. And here I've got particles of a couple of different sizes. Yes. The whole screen is gone. Let me try the next slide. And is that now visible or not? Okay, then I have to try and reshare, I think. So I'll unpresent, stop presenting. I'll try to present again now. And I hope this will now be visible. Has that come back? Okay, so obviously interrupt again whenever that happens. It maybe the movies are upsetting it, of course. So what I was showing on the previous slide, which I won't try to do again in case it again undisplays itself, is on the right-hand panel I had a computer simulation which is in 2 dimensions, hard disks, which again showed this very erratic and jerky flow behavior. So shear thickening suspensions have this property of becoming jammed so that the particles can't flow freely past each other. And they tend to do this when you subject them to a large stress. And the canonical example is cornstarch. If you go to the supermarket, buy some cornstarch, so it's a white floury substance, and you add a little bit of water, you will achieve, if you keep adding water until you can only just see it becoming wet looking, you'll get a material which is like you see in the left picture here under this person's foot, which is like a paste, but it's quite fluid if you stir it with a spoon extremely gently. But if you try to firmly stir it, it actually jams. It stops being flowable. So this jamming transition, it's so-called, can either be continuous, so-called continuous shear thickening, or discontinuous. In other words, as a function of the stress, you can either get a smoothly upward curved, as a function of the flow rate, you can either get a stress which increases smoothly, or you can get a stress which jumps. We'll see examples in a minute. So this material is called Oobleck, at least in the USA, based on this book here, which is about a young boy who has interesting experiences with non-Newtonian fluid. And many of you will have seen it in your kitchen, or you'll have seen it at demonstrations. And this is this, I hope you can see this one, a YouTube video of a guy who's now about to run across a large bath of, that is cornstarch solution. And you see the other guy has sunk into it. So if you run fast across the top of this, you don't sink in. It's basically a solid. If you move slowly, you sink in and get soaked. So here's another rather bizarre thing, which is the Daily Mail, who some years ago now reported essentially it's a high-tech version of cornstarch, the same principle, shear thickening material, which has been used by someone called Norm Wagner in the University of Delaware in the USA to design bulletproof clothing for the army. And that's because it's a fluid, so you can move around in it, but if you hit it hard with a big stress like a bullet, it solidifies immediately. That's the idea anyway. So here's some experimental data about this. This is a log-log plot. You see on the bottom a shear rate which is going between about 1 and 100, or 0.1 and 100. So the units of shear rate are per second, because the strain is a dimensionless variable. It's telling you the percentage change in shape, if you like. So and you see on the left column again log plot stress. And the interesting thing here is that if you have a almost Newtonian behavior down here, you reach some, in this case it's discontinuous, you reach a critical level of stress, or equivalently a critical shear rate, where you jump up by 2 or 3 orders of magnitude onto this other behavior up here. And then if you start slowing the thing down again, or you back off the force that you're applying, you jump back, but you jump at a different place. That's called hysteresis. And that's usually a signature of this discontinuous behavior. So here's some more precise data, which was measured by a collaboration in Edinburgh, where I used to work until 2015. And there are various flow curves, the stress as a function of strain rate here on the log-log plot. And these are for different volume fractions. So the volume fraction is a jargon term. It's basically telling you how much of space is filled with these particles. So these suspensions, what I'm talking about, are little solid particles living in a liquid solvent such as water. I should have been more clear about that. And for a theorist, one tends to think of them as spherical. So the volume fraction is the amount of space, the fraction of space that comprises solid spheres as opposed to the surrounding liquid. And this evolution, say between this smooth, continuous shear thickening curve on the left and this one, say, which has this, or the green one actually is the first one to show essentially a discontinuous transition here. So you have a vertical section on this line, happens in a range of volume fractions between about 50 and 65% of the solid material in the liquid. If you have a random packing of spheres, for instance, the maximum you can get in is only a bit above 65%. If you pack the spheres into some kind of crystalline lattice, then you can get up to 70 or 80. So what I want to show here, though, is that if you look more closely at the behavior now as a function of time, you find, so this is one of these curves in blue here. What you find if you apply, I shear the sample at a certain rate in a device called a rheometer. So I set up a certain rate of motion of the boundaries of these plates, if you like, and look at what's happening to the stress, to the force that I need to apply to do that. And what you find is that once you get into this kind of vertical piece of the curve here, firstly, it's very erratic, but secondly, as a function of time in this region, the stress is jumping around all over the place. And what's shown here are, if you focus on the colored curves, various different time evolutions of the stress. So you can get something which seems to be steady and then has a giant deviation, something which has oscillations. This one has got some kind of intermittent oscillations, and this has got random looking behavior, which is called chaos. So these, not only then in these materials do I have this a possibility of a sudden change, a massive increase in stress at a certain shear rate, but in that neighborhood, I see these unsteady, jerky behavior of the material as a whole. So that's the kind of experimental situation. And the question I first want to address is how, in the simplest possible terms, can we explain this rather complicated behavior? So the first thing I want to do is to say that the complicated jerkiness and this time-dependent behavior can be explained if one postulates a certain shape for what I call the flow curve, which is the steady state stress as a function of a steady shear rate, were you able to apply one. So I take the hypothetical situation where I somehow enable the system to flow smoothly and ask what is the relation between stress and flow rate or rate of strain in that situation. So that, what I'm going to do now is draw a bunch of these flow curves, hypothetical ones. Each curve corresponds to a higher value for this volume fraction phi. So starting with something around 50% of solid particles in water, say, and going up towards this 65. And the first curve I've drawn here in purple is Newtonian. That's a straight line. But this whole scenario with this complicated series of behaviors that I showed on the previous slide would all fall into place if the basic thing that the system is described by is a steady state response, sigma as a function of gamma dot, which has this evolution as a function of volume fraction. So I'm going to put some extra curves now, each at a higher volume fraction than the previous one. So if the curve started doing this, and then I increase, say, 55, 56, 57, 58%, and I saw this sequence of curves, and the last of these is called full jamming, then it turns out that all of that complicated behavior would be explicable. For instance, if I focus on this curve here, what I've got here is a system which has a steady stress as a function of the strain rate gamma dot, which is S-shaped, And the first comment is that in the middle of that S shape, I've got a region, the dotted region, where this has a negative slope. And that means if you think of sigma is the force per unit area, gamma dot is the speed at which things are moving. If I have a negative slope here, that says that if some part of the sample moves fast, then the force on it goes down, so it's going to move even faster. So the negative slope gives you a positive feedback between going, if a patch of fluid is able to shear faster than its neighbors, that has positive feedback under conditions where this slope is negative. So this is why you expect in a region of stresses in this kind of window here to have unstable behavior, which leads to all these oscillations and chaotic stuff. But the other thing is that this curve also explains what I called hysteresis. If you do come up this curve, so what I'm doing now is progressively increasing the strain rate and measuring the stress, for instance, I'll get to this point here and then there's nowhere to go. I try to increase the strain rate, and the only way I can flow the system any faster is by jumping right up to there. So that can be your factor of 100 or 1,000 increase in the stress as over essentially infinitesimal increase in the rate of strain. So that's a sudden jamming. I'm trying to make the system flow a little bit faster and suddenly it locks. And so the stress I have to apply goes up by orders of magnitude at that point. But then once I'm on this upper part of the curve here, I can back off the strain rate. The stress will come gently back down again, or at least there's a chance of this happening, and it can come back down to that point before it has to jump back down to the lower stress. So the multi-valued character of this curve is able to explain the hysteresis. So the instability of hysteresis and all the other phenomena I talked about also can be explained this way. So that's what it says here, and don't worry about what these other things mean. So it's these S-shaped curves which I'm primarily interested in today. Just out of interest, though, this last curve here, which I called full jamming, this is one where I have the S-shape has met the vertical axis. And this is a fluid down here. And in this case, there is a stress, a critical stress, above which it will simply not flow at all. So that is a fully jammed material. It becomes a solid. And the only way that can flow is by actually fracturing. So it will actually break. And if you get your little pot of cornstarch, which you make in the kitchen from the white powder from the supermarket and a small amount of water, it's quite easy to get into this regime. You start stirring it with a spoon and you get to a point where you feel this huge resistance against the spoon, and then beyond that, it actually breaks apart. So all of this falls into place if I have this evolution of the non-Newtonian flow curve stress against strain rate. So what is the problem and why am I giving a talk about it? Well, I said this. What I need, though, to get a strain rate, a flow curve like this, there has to be some characteristic scale of stress or of strain rate, which we can call sigma star or gamma dot star. There has to be some physics in the problem, which one way or the other locates where this kink in the curve is going to sit. And there's an issue with that. And the issue is that for probably the last 3 or 4 decades, the physicists and mathematical modelers in this field have been using a kind of standard model, which effectively corresponds to microscopic ping pong balls in a Newtonian solvent, which with a certain viscosity A to S, such as water. And if I've got these things, the standard model is that they are hard spherical particles. So I have a viscous solvent, and the dimensions of viscosity are mass per 1 power of mass and the inverse powers of length and of time. And it turns out that if I have a solvent with a viscosity that's water or any bigger, and I have particles that are smaller than 100 microns, inertia is negligible. I'm in this regime which is where if I have a particle and I push on it, it moves with a speed proportional to my force, but if I stop pushing, it essentially stops moving immediately. And that's because the viscous forces vastly outweigh the rate of change of momentum of the particle. So without inertia, there isn't another mass. And the other thing which is also negligible, this time for particles which are larger than about 5 microns, so on this big window of particle sizes, which certainly includes cornstarch, then Brownian motion, which some of you will know about, is negligible. The Brownian motion is the random motion of particles caused by the fact that they're in a solvent at finite temperature, so they're getting bombarded with random molecular collisions. So without Brownian motion, there isn't another time scale either. So the only things that I've got are the viscosity and the radius of the particles here. And if the particles are hard, then what I mean by that is that as a function of their separation x, there's no force until they come into contact and try to overlap, at which point an infinite force keeps them apart. So the hard sphere assumption means there isn't any dimensionful quantity associated with the force law either. So this scale-free interaction gives me a length from the particle radius, but not a time. And the force, again, gives me the same length and still no time. And because of that, out of those quantities, I can't find a characteristic scale of stress or rate of strain from the things I have at my disposal in my physical description of this problem, which is the radius of particles, the fraction of space filled with particles, so that's the volume fraction, and the solvent viscosity. So that's a kind of no-wiggle theorem, and it leads to the following conclusion, that if I have a suspension of hard particles, they needn't be spherical, in fact, but they have to be hard, in this regime of sizes where there's negligible inertia and Brownian motion, all I can get is either a Newtonian fluid, so something with a finite viscosity and a straight line relationship between stress and rate of strain, or the only other case is that this can be completely jammed, so that the viscosity, the slope of this curve can be infinite. I have a stress which is divergent for any finite steady rate of strain. So it's conventional to think of the actual viscosity, which is the slope of this curve, of the suspension. You take out one factor, which is that of the water or the solvent. I'm left with a dimensionless thing. So that's S, which depends on phi. So what happens as a function of the volume fraction is that I have a Newtonian liquid whose viscosity, i.e. the slope of the curve on the left, is doing this thing on the right. And then at some point called the jamming point, so at a density of particles, I can't go any further. Yes. Okay. Sorry, is it back, or do I need to Okay. But at the point phi j, which is maybe around 60%, I have a solid. Okay, but that's not what I want to explain all the physics I said before. However, it does expose this key parameter. Yeah. It's okay, so should I just go out and come back in? I think I better do that. Sorry about this. Unpresent. Present again now. A window. Hopefully that's come back, has it? Okay. Okay, so there's this key thing which is called the jamming point. That's the volume fraction at which you can no longer move. Now, what governs that? And it turns out that the physics which governs the maximum density of particles at which flow is possible and beyond which the system is always jammed is the friction at contacts between these hard particles. And this is possibly surprising because there's essentially a theorem which is due to the 13th Lucasian professor, which is Stokes, which is that if I have hard spheres specifically suspended in a Newtonian fluid with a no-slip boundary condition, these particles never touch each other. And that's because as I push them closer and closer closer together, the force I need to apply to squash out of the way the fluid that lies in between becomes bigger and bigger. So you might think that there's no role for friction between particles in a dense suspension, at least of spheres. But this turns out to be a simplification too far. And however, it's one which, because it was lurking in people's minds, probably delayed the understanding of this field by at least a couple of decades. So really, we've only understood the role of friction now for about the last 7 or 8 years. And evidence for this comes from an experiment where you get a system which can flow, and you suddenly reverse the direction of flow, and you measure the stress, which here is called tau, divided by the steady state stress. So under a system which had this kind of so-called Stokes behavior, where in that system where all you have is particles and you have fluid and the fluid keeps the particles apart, it turns out that if you reverse the flow, all of the forces reverse sign and do not change magnitude. So that if you reverse the flow, the shear stress changes sign but does not change value. And that is physically not true. So in a suspension of, let's say, 50 or 55% volume fraction here, you find that the stress collapses to about a third or a half of its steady state value. And then as a function of time, as you go on, as you continue to shear it, goes back up to the steady state value. So the data for the presence of contacts has actually been around, turns out, since 1980, but nobody quite understood its significance, or many people didn't understand its significance at the time. So why does friction matter here? So on the left here is a clip from, or just a frame from the movie. I've got these particles, which the red lines here, I never explained what they were. Those are the lines connecting the centers of particles which are actually touching. It looks like more particles are touching, but that's because of the resolution of this picture. Other particles don't have direct contact between particle to particle. So you can ask whether a packing like that is a rigid object. And this type of question was first addressed by James Clerk Maxwell, who was the first Cavendish professor, for the physicists among you, who was thinking about structures like this one in the middle, Fourth Rail Bridge. How many struts do you need to attach to one another, and by what kind of joints, before you get a rigid construction? Now, the application of this to dense suspensions requires a shift of mindset, which was introduced by Sir Sam Edwards, the 8th Cavendish professor, and as it happens, my PhD supervisor many years ago. So you take a packing of particles now, and you say, how many contacts do I need for that to be rigid? And I have to think now about the nature of the contact. If I have friction between the two particles, that's a contact which can only roll. In other words, rough particles, if you like. And so then I have a constraint on the increments of the angle and the separations between the particles. Separations can't exceed contact, obviously. If I have particles which are freely sliding, so two particles which are in contact across, for instance, a thin lubricating layer of fluid, then I have a constraint on the separation, but not on the angles, not on the increments of the angles in any particular motion. So you can solve this problem. Sam Edwards did it. If you have a certain number of contacts per particle, which we call Z, the coordination number, which can fluctuate, but this is the average value I'm talking about, which depends on the density of particles, and I have a fraction f of these contacts which roll, then at these contacts I have two constraints on the motion. And at the other contacts, so 1 minus f fraction of these contacts can slide, and only one constraint. And it turns out then, there's this equation at the bottom, that the number of contacts per particle, when that exceeds this expression here, where d is the dimension of space, so 3 is the usual case, but you can also do it for 2 dimensions if you're thinking about disks. When that exceeds that linear relationship here, so that's plotted on the right, if I have, depending on the type of friction or the fraction of frictional contacts, if they're all non-frictional, then I need 6 contacts per particle in 3 dimensions to make a rigid packing, and if they're all frictional, I need only 4. And since the number of contacts depends on the volume fraction, that's why this jamming point, phi j, that I described, depends strongly on the character of the friction at the particles' contacts. So if I take a random packing of particles and I look at what the coordination number actually does, that gives me a jamming point, which I call phi r, if you like, for rough particles at 58% volume fraction, so 0.58 with full friction, so all particles, all contacts rolling. If they're all sliding, that moves up to 64%. Now, that may not look like a very big difference, but it really matters for understanding dense suspensions, and it matters when you're making the kind of things like chocolate and things I hope I'll have time to say a little bit about later. Okay, so here's where we got to so far. If I have hard particles, I must have Newtonian behavior, but the slope can be infinite, and it is the jamming point where the slope is infinite is at a friction-dependent threshold, about 58 for rough particles, about 64 for smooth ones. In purple here is something which is in between because it has, say, a coefficient of friction between the particles, which is maybe 0.2 or something like that. So with a fixed coefficient of friction, a certain fraction of the particles will be sliding at any time. So I have this. Now, what I still don't have is this scenario here. What we want as a function of volume fraction, we don't want a bunch of straight lines. We want a bunch of lines which become increasingly kinked. So nonetheless, with the bits of physics that I've assembled for you, which is the Newtonian part and the friction-dependent jamming point, it's only a very small step now to get these curves. And that's to go one step, a small step beyond our standard model, and admit that in reality, the particles, say cornstarch, they're not spherical, of course, but the key thing here is not, in this case, whether they're spherical, it's whether there is a additional force that is not described by a hard sphere interaction. So I mentioned the characteristic of the hard sphere is that I get a characteristic radius, which is the particle size, but there's no scale on this force curve in blue. If I have any other kind of short-range repulsion, and in a system of particles in a solvent, there's all manner of mechanisms which can give me a short-range repulsion. This has been known throughout. It's just for many years we thought, well, there's not so much difference between that dotted red curve and the blue one, which has just got this vertical wall. But now it really matters because that additional short-range repulsion gives me a force scale, which is the force that I need to push two particles together to actually make them come into contact. So that gives me a stress scale. So just dimensionally, I take that force scale, which is the force I have to overcome to push particles into contact, and that gives me a stress scale. If the stress in my system is much less than that characteristic stress, most of my contacts will be frictionless because they will have a layer of film of fluid still in between them. If I increase the stress above this characteristic, far above it, most of the contacts will be frictional because I will have ruptured any fluid film between the particles because I'll have overcome this characteristic F star force. Okay. So this is a theory. It's a mathematical theory, and I can show you the equations to prove it, but the easiest way to understand it is just in terms of a series of graphs. So on the left is a two Newtonian flow curves, so straight lines, for what I'm considering here on the right. So if you consider the same system, or two systems which differ only in the fact that one of them has friction between contacts and the other has sliding contacts. So frictional in blue, sliding in green. So each of these would be Newtonian if that was all that was happening. But now I introduce this idea of the stress scale, and I say that if I'm well below sigma star, I must be on the green curve because I don't have friction. If I'm well above, I must be on the blue curve because I do. So I can draw these horizontal dotted lines for instance, at half sigma star and 2 sigma star, but you can make them epsilon sigma star and enormously large number times sigma star if you want. The physics that I'm about to describe will still work. So I have that, and I say, okay, what should this system do? Well, I should get the red curve here, which starts off on the lower Newtonian straight line, and over an interval of stress switches to the upper one, because this is the window within which I have a transition, a smooth transition from frictionless to frictional contacts between the particles. So that's very simple, and that gives me what I described previously as continuous shear thickening. If I do it as drawn, that red line is has upward curvature in the middle, but is not actually kinked. However, what I'm now going to do is march the volume fraction, so the actual value of the particle density here, to the right, towards phi r. And I must get this sequence up a bit. So the slope of the blue curve has gone up a lot. The horizontal line at 2 sigma star, say, is in the same place. So this must get steeper. The green curve has hardly increased in slope because I'm nowhere near the divergence here for the slope of the green curve, which is at phi s, which is much higher. So I just keep going, and you can see what's going to happen. This has no option but to curve backwards and give me an S-shaped curve. And if I carry on, and I reach the point where I reach phi r, beyond which, in the frictional case, there is no flow, then I have full jamming. So if I wind back through that, this series of curves that I'm sketching out now, which is the combination of Newtonian plus friction that depends on stress, gives me exactly what I wanted, which is this series of curves with the S shape and then finally culminating in full jamming. So that's what we wanted as a function of phi, and so the scenario that I described earlier is explained in that way. So I like this a lot because this is an example, if you like, of graphical mathematics. You can explain this essentially without equations. Of course, though, we do equations as well, and if there's time, I'll come back to that a little bit at the end. So I don't want to say anything about that, except to say that you can check this out with computer simulations of actual particles. And in the computer simulations, you can see whether there's friction at individual contacts. You can say the contacts switch on their friction above a certain force between that pair of particles. This behavior, the friction as a function of stress, is completely smooth. But it's the combination of the smooth evolution of how many contacts have friction with that depends on that on stress. That's smooth. All of the other physics is smooth, but the combination with that and the divergence at phi r gives me these kinked curves, and they can lead to these sudden jumps, hysteresis, etc. So if you remember what I said before, with the curve on the left, I come up the red curve, I have to jump suddenly up to the higher branch. If I come down, I have to jump down again. That's discontinuous. And you might think, oh, well, this is all very simple. But it would be perfectly possible to think of a system in which the forces between the particles, the friction, wasn't dependent on the state of friction was not dependent on the stress, so on the force, but on the speed at which those particles were moving relative to each other. So then I'd have a very similar thing. I'd have a frictionless Newtonian curve and a frictional one, which had to join up. But now these dotted curves here would say, well, if I'm going fast enough, I must be on the frictional curve, and I'm going slow enough, I must be on the non-frictional curve. But you see, it doesn't matter how steep the blue curve is. If I had this scenario, it would never fold back. So the fold here, which gives me all the physics I wanted, is specifically connected with a stress-dependent friction, not a rate-dependent friction. Okay. So let me move on to part 2, which I will have time to say something about, and I may get into part 3, but I certainly won't have time for part 4. So one of the things why this work matters is because these suspensions are used a lot. So one thing we want to be able to do is to avoid jamming in dense suspensions. And let me exemplify. Well, firstly, let me say what the idea is here. So let's suppose I can find a magic molecule that when I add it to my dense suspension, essentially removes the friction at contact. So for instance, I could have rough particles that when I add this molecule, it somehow coats them and they become super smooth and slippery, whether or not there's a liquid in between. And so the friction is abolished. So if I start with the original scenario here, this series of curves here, and I reduce the strength of the maximum friction I can have by adding a magic molecule called a friction modifier, then what it does is it basically moves phi r, this first jamming point, it moves that to the right. And as I do that, these curves collapse. And obviously, if I go so far with my wonderful magic molecule that it's always perfectly frictionless, I go back to the original Newtonian scenario with no friction at all. So having got this rather complicated shear thickening behavior, which in an industrial setting I nearly always want to avoid, the fact that it is caused by friction suggests that one uses or tries to find molecules that change the actual nature of the frictional contacts. So let me frame this with an example. Chocolate. So chocolate is made in the molten state, which I'll show you a picture of in a minute, through this process called conching, which is actually a stirring process. So it's a flow process of molten chocolate. And you start with a bunch of ingredients and you make chocolate this way by conching. And this is a paper that we wrote on this, claiming that essentially the manufacture of chocolate by this conching process is directly related to what I've just been talking about. So here's a theorist's cartoon of what is in molten chocolate. You have a continuous liquid, which is the melted cocoa butter, which is actually fat. So that's an oil, but it's Newtonian. I have solid particles, which obviously here are not really spherical, but drawn so for simplicity, comprising cocoa solids, sugar, and if it's milk chocolate, you also have skimmed milk powder in there. That's normally the way chocolate is made. You might think it involves milk, but it actually, you have milk powder. This is, I hope you can see this movie, this is flowing chocolate in this conching state. And one thing you may be able to see is that this flow on the surface has these kind of streaky, cracky appearance. And that's because this flowable fluid system is really close to jamming. It's got about as much solid as you can possibly put in before it jams up completely. And you might be interested in the fact that many chocolate companies are desperate to increase the solid content further. This is to allow them to add more sugar, which paradoxically reduces the calorie level of chocolate, because fat, cocoa butter, is one of the few things which has even more calories per unit volume than sugar. And there are many interesting ideas about putting in things there which are neither fat nor sugar to produce kind of less bad for your health chocolates. Now, if you just buy a bar of chocolate, this one came from the US, but you'll see on it some mysterious ingredients called emulsifiers, soy lecithin E322, polyglycerol polyuracil oleate. And what are these? Well, we understand now what they are. They're molecules which you put into this system, you mix them in, they go to the surface, and they reduce the friction between these particles. So these allow you to have more solid in your melted chocolate without it jamming up. This is not just true for chocolate. Here's a kind of generic drawing. If I have something like, yes, okay, I'll just go away again and come back again. Seems to be the only way to do this. Does that come back? Okay, right. So setting cement is, I could draw, there'd be different identities for these different particles and different, I mean, that's got a different solvent as well, of course. They're things, the kind of thing that you mold, sorry? Okay. Right. Oops, I shouldn't have done that. Excuse me, just 1 minute. Now, what am I looking for? So, stop presenting again. Presenting in now. Unfortunately, I had to go back to the beginning just then, so there's going to be an annoying minute now. Let's see what's the best way to do this. Go back roughly to where I was. It was here. So I hope you can still see this. Okay, so there are a whole bunch of industrial systems where you want to handle.
So I can't still see it. I don't
okay.
Now it's
sorry?
now I see it. Now
it's come back. Okay.
Yeah, let's hope it's.
Well, interestingly, now I don't see. Oh, you can. Okay. So these systems are all over the industrial world. It's to do with having as much solid as you can in a formulation and still have it flow. So these things are on. If you read your chocolate packet, they're called emulsifiers. They're called that in many other industries as well. But in fact, if you know what an emulsion is, they're not that. They don't emulsify anything. They reduce the friction at contacts. And once you know that, you should be able to formulate better molecules and better systems for reducing this friction.
Excuse me, sorry for disrupting, but the screen disappeared again. Could you please again try to share it again?
I don't know. I really don't know what's going on here, by the way. Okay. Is that still there?
No.
Should have come back.
Sorry? No, unfortunately, I don't see it.
Well, let's not worry too much about this because I am close to the end and I can probably do the rest of my talk without slides if I need to. But I will, before doing that, I will just try one more time to get this to work. Let's see if I try presenting my whole screen instead. Can you see anything now?
No. I don't know where is the problem. So perhaps.
Well, let's not worry about that because it's close. It's nearly 7:15. So I'll just what I'm going to do is just say a few things in words. And this is about the kind of wider implications of this work. First thing I want to say then is that I've shown you this theory, which is it is a theory about how this shear thickening phenomenon happens. And as I've said, you generally want to avoid it, and then we've come up from that with a strategy to avoid it. So in words, I want to just say a little bit more about other strategies to avoid the jamming. And one of those, which again has a sort of a long history, but without necessarily being entirely understood as to how it works. If I have a dense suspension like cornstarch and I am trying to flow it, but it gets jammed, it's a natural strategy to basically try and shake it into flowing again. And you might ask, well, what's going on there? And what happens is that in the jam, these particles come into contact, so they develop friction at the contacts. And the kind of more scientific way of thinking about shaking in a physics lab experiment is you have a steady flow, like, and I don't know if you can see my hands. Can you see my hands? So I'm shearing like this, and then on top of that, I put an oscillatory flow into the in the opposite direction, in the perpendicular direction. And what the oscillatory flow does is to open contacts between particles. So it unjams the system. And so a lot of what we've been working on recently is, you see, what I've told you about so far with these kind of graphical maths is basically a theory of the steady behavior. If I start doing this oscillation, that's not steady, and I need to go to a more complete mathematical description. This involves using a tensorial description. You have a stress tensor, you have a rate of strain tensor. So things rapidly get relatively hair-raising on the in terms of the formal structure of it. But what you're doing is building a model that can cope with this idea that I can have, if you like, two flows at once in different directions. One can be oscillatory, the other can be steady. And the secondary, or the oscillatory flow, what it can do is can break open the contacts and reduce the friction, which unjams the main flow. So this is important. For instance, if you are, say you have one of the, let me just mention one other example of a dense suspension in use. If you break your bones or you have a hip replacement, then there are conditions under which a surgeon wants to glue together either a metal hip replacement into a bone or bone to bone. You have an adhesive. Now, obviously, this adhesive is very carefully formulated to be compatible. It's got cells and things in it that allow the bone to regrow. And what you can't do is start, adding some ingredient that you found was useful in chocolate to that, because it'll probably kill you if you put it into your bone. So this other strategy, which is to have a flow protocol, this is what we call contact engineering by a flow protocol, by essentially choose. So if I'm trying to syringe this very dense suspension of this glue into a cavity to do this procedure, then what I need to do is I need to design a syringe, which the device which I'm using, if I have that so that it's got a vibration on it as part of how that thing operates in a perpendicular direction to the way I'm trying to get the suspension to move, then I can get it to flow at under conditions where it otherwise would be jammed. So, as I say, there's a whole theory of that, which I would be tempted to say more about, but it's probably quite convenient that I can't show my slides because this is anyway when the talk ought to end. So I hope I've shown you some things that are of potential interest, admittedly a bit maths-free in the end, because the slides didn't last as long as I'd hoped to get as far as some of the beefier equations. But as I said earlier, one of the things I like most about this field is that at least part of it, so this description of how you get an S-shaped curve from combining stress-dependent friction with otherwise Newtonian behavior, is demonstrable graphically, essentially. And what that means is that the details of those equations don't matter. I could have all kinds of sophisticated models for how the exact fraction of frictional particles depended on the stress level and so on. Doesn't matter at all. That basic scenario is incredibly robust because it's something which I can understand essentially just using sketches and effectively topological arguments about how these curves have to evolve when I change a parameter, in this case, the particle density. Okay, so sorry about the technical gremlins, and thank you everybody for your attention. And I understand that we stop now, and then there is a chance for Q&A for those who want to participate.
Professor Cates, thank you for a fantastic talk. Now it's time for a Q&A. So if you have any questions, you can join our video call using the link below, or you can type your questions to the chat and I will read them. One important thing, before you join the video call, please mute the video on YouTube. the sound from the video might be transmitted by Google Meet and get looped through the live stream. Please feel free to ask your questions. Yeah, we have one question in the chat from Christian. I would like to ask, what are the implications for extensional flow?
Extensional flow. Okay, excellent question. Well, one of my collaborators, whose name is Chris Ness, who was in Cambridge until last year and is now in Edinburgh, has looked at that. Yes, so shear thickening can definitely occur in extensional flow. So the usual simplification is you work in a sample whose volume is assumed to be fixed, which is perfectly appropriate when you have particles of fixed volume in a solvent of fixed volume. So the extensional flow is one in which you're essentially stretching fluid without rotation, whereas shear flow combines stretching and rotation. But it's actually the stretching, the fact that you're stretching fluid along an extension axis and the fluid is coming in the other direction or directions, that's actually the important part anyway in terms of creating contacts. Extension breaks contacts, but if you have fixed volume and you have an extension axis, you must have compression in the other directions, and it's that compression which creates contacts between particles. So even in a shear flow, you can identify a compression direction of the flow, and that's bringing particles together. So I didn't talk about extensional flow. In principle, one could expect a set of flow curves which would be a stress versus extension rate, and they would be qualitatively extremely similar to what I drew for shear. All of the quantitative details would be different, but for the reasons I said at the end, this is really a very kind of robust, almost topological argument. Then you expect the same kind of things to happen. So you expect if you pull at a steady extension, or you have an extensional flow between rollers or whatever, it can jam with essentially the same physics as I've described.
Yeah. Great. Thank you for your answer. We have another question. This kind of curves are well known in optics from nonlinear optical materials. They were proposed for optical switches. Further, there are also multi-stable states with multiple jumps in S-curves. Do we have such multiple jumps here? If not, why don't we operate above the jump where things look smooth? It's also
okay. And I can see the chat. So yeah. So yes. So when you say multiple jumps, are you talking about several wiggles on the same material, or just one S-shaped curve that you can do more than one thing with? I'm asking a question of the questioner now, so there's no reason that they need to answer. Okay, well, let me answer anyway. So there are certainly examples where you can have more complicated curves than I've described. And for the curves which are S-shaped rather than going to full jamming so that you have the ultimate high-stress babies totally jammed, you ask, why don't we operate above the jump where things look smooth? So you mean above the last jump or to the right of the jump? Well, yeah, okay. So several jumps. Actually, I don't know. There are systems where you get more than one wiggle. I'm not sure of any where it's established that there are several jumps. You could design. Okay, I'm sure I could invent a hypothetical system with multiple jumps, because I could invent an interaction law where I replace this short range repulsion. I can replace that with a kind of stepped, interaction that has different you have different thresholds. So I think I could probably come up with something like that, but whether that's practical, I don't know. If you have a system with attractive interactions, then, which I didn't talk about at all, but then actually you have a more complicated flow curve, which starts off with shear thinning, because when you add a bit of flow, the first thing is you break all these bonds that you've got in the attractive interactions, and then at some higher strain rate, it has the S-shaped stuff. Operating above the jump where things look smooth is a sensible suggestion if all you want is smoothness. But what you're doing there is you're flowing a system by applying a really high stress. And this costs a lot of energy. So say you were making your chocolate, one thing I didn't mention actually, and that project on chocolate was actually funded by a chocolate company. One of their main interests, apart from avoiding this jamming and intimately related with it, is you want the processing to be done. And if you're making chocolate like that, the conch can be it can be hours long. And you actually want to be doing that at the lowest stress that you can, that achieves the final state that you want, because the energy cost of that process is quite a big contribution to the cost of a bar of chocolate. And it's certainly a huge cost to the carbon footprint of a chocolate company. So above the jump, it's good for stability, but it's very bad for the total energy cost. And one of the things I didn't have time to say with this vibrational tactic, there's this idea of having a main flow and a transverse vibration to unjam it, is that to get the best energetics out of that, so to get the overall flow of the system at the lowest possible energy, what you actually should do is you should flow it a bit in the forward direction and then stop and apply the oscillation and then flow it again. Because if you have the two actually superimposed at the same time, the stress is quite a lot higher than it needs to be if you do an alternation of forward, sideways, forward, sideways.
And so thank you for answering the question. And I have one more about the question. Let's say if usually one does avoid these kind of things, but it's purely of academic interest. If we have some resonances in some system where we are trying to do this kind of an experiment, and all of the resonances will be shifting because of this kind of, will they be shifting because of this kind of nonlinear behavior? How would they be affected in such a case?
So, I mean, okay, so talking about resonances, again, I can see where you're coming from in terms of the optical materials. I'm not really sure what the counterpart of resonances are in the systems I'm talking about. If you have a device in which you are flowing this shear thickening material, then you can get mechanical resonances of that whole device. And if you have a shear thickening fluid in there, that's when you get, you're trying to mix concrete or something, that's when your machinery starts juddering and really causes problems. I mean, that's when actually big industrial machines can literally break under those conditions. So I'm not sure whether there's really a connection between that and the kind of resonances you're talking about, but it's the nearest thing I can think of in this kind of mechanical domain of flowing dense suspensions.
I see. Thank you. Thank you very much.
Thank you.
So there are three more questions in the YouTube chat. So I will read them, and maybe perhaps then we can finish after these three questions. First question. What would happen in a situation such as surface tension instabilities as the Rayleigh one? Any changes in the pinch of dynamics?
Excellent question. So one of the interesting things which I sort of mentioned in the context of that chocolate, where I talked about these kind of crack-like striations on the surface. if you have a free surface flow, when I was talking about the original problem, I just talked about a sandwich. I have 2 plates and a block of this non-Newtonian fluid in the middle. If you have such a fluid with a free surface, then there's a very strong and interesting coupling between the surface physics and what's happening in the bulk of that fluid. And the way this shows up is if you get, say, you get a cup of cornstarch or like that kind of huge tank that the guy was running across, and you prod it, you look closely, then in the fluid state, the surface is shiny. And you can, if you prod it in the neighborhood where you're doing that, the particles in the fluid beneath jam, and the surface looks dry, it looks matte. So accompanying the jamming transition in the bulk is this big change in the surface behavior. And this is to do with the what are called normal stresses, which I didn't talk about at all. When you shear a non-Newtonian fluid, as well as the shear stress, which I described, which is the horizontal force on the top and bottom plate, if it's a shear thickened fluid, those plates also get a force pushing them apart. And that interacts with the shape of a free surface in a interesting way. So in particular, again, another thing that happens if I have there's something called a cone and plate device, which has a flat disc and then a cone on top. And this is a typical experiment for measuring the kind of flow curve that I was talking about. And you're usually relying on surface tension at the edge of the sample to hold it in place. So you can be in the low viscosity region, you can be rotating this cone on top of the plate, and there's flow everywhere, of course, and you have this meniscus. And in many cases, once you start jamming, the meniscus goes horribly unstable, and very often the whole sample just jumps out of your device. So there's definitely a connection there between the two things, but we don't really understand exactly how those two bits of physics join up.
Yeah, thank you. So I will read the second question. Do electrolyte solutions impinge on ways to modulate thickening?
What was the second word? Do what?
Do electrolyte solutions impinge on ways to modulate thickening?
Electrolyte solutions,
Yeah,
yes, they do. Because I talked about these soft range repulsions, short range repulsions. In water particularly, and in fact, indeed, in the case of cornstarch, that is a electrostatic interaction. It's because the particles are weakly charged, and there are countercharges in the surrounding solution. So what you can do is you can add an electrolyte or salt simply to the water in this case, and that changes the range and the strength of this soft repulsion. So, and it's true in many colloidal formulations that, as well as adding molecules, controlling the forces between particles by changing the ionic strength or the related properties of the suspending fluid is another way of tinkering with the behavior. Yes, that's true. Doesn't work in chocolate though, because it's an oil in the continuous liquid phase.
Yeah, great. Thank you for your answer. And the last question is, how do gems within the same substance interact with or affect each other? How does a gem propagate in a material? Sorry.
Yeah, excellent question. So yeah, so the whole of my you saw a little bit of that in that the first movie I showed with the right-hand panel, where there were particles that were periodically jamming and unjamming. So yes, so throughout the talk I talked as if the material was always homogeneous, but I did show in the experimental part these kind of very complicated time dependence of the stress as a function of T. And what I didn't say, but could have done at the same moment, is that I do have a complicated spatial variation as well. So it's quite possible to get a system which is flowing along, some part of it jams, that then becomes like a rigid inclusion, which then starts rotating, and then some other bit will jam as a result. So there is a kind of avalanche effect that is involved when say as a function of time, a material goes from a flowing state to a jamming one, which is what's happening in those complicated time dependencies. And it may nucleate at some place and propagate out like some kind of avalanche where the frictional contacts spread through the system. A bit is known about this kind of avalanche, not specifically in relation to the jam. Well, it is jamming, but it's not the switching on of friction. It's just if you're in a system which doesn't have stress-dependent friction, but if you're very close to phi r, to the jamming point, and you ask what happens if you push on a particle, then you do get a disturbance which spreads out a long way. And so there's a whole area of physics to do with these kind of static avalanches, which I didn't talk about and which we're not really on top of, in the sense that we don't know how to reflect that complicated physics in the kind of models that we have.
Good. Professor Cates, many thanks again for your great talk and answering the questions.
Thank you very much indeed. Sorry about my screen sharing problems, which are probably at my end. And I hope, well, at least we got through most of the talk without my having to basically speak equations at the audience, which wouldn't really be a very good strategy. So thanks very much indeed, and see you sometime. Okay. Bye for now.
Next Thursday, there will be a talk by Dr. James Herbert Reed, a marine biologist from Department of Zoology here in Cambridge. He will be speaking about coordination of movements in schools of fish and other animal groups. These complex behaviors arise from simple rules followed by individuals. The talk is going to start at the same time as today, next Thursday, 6:15 British time. Thank you for attending the talk and have a nice evening.